Okay, let us continue our analysis of CS amplifier. Now we know that this is a CS amplifier. We have these are the equations which are governing the CS amplifier. We have the drain current equation given by this. Of course, this is certainly in saturation because whenever we discuss amplifiers, MOSFET has to be in saturation. So even though if I don't write ID sat, it is the current in saturation condition. And this VGS is realized using this R1, R2 and VDD using this equation. And we have the small signal gain as minus GM into RD, where GM is realized using this particular equation. And if I just list out the key parameters that we have, so we have kappa, that is transconductance, and we have W by L of the transistor, we have VTO, that is threshold voltage, and we have, I'm just writing each and every term, and we have a RD here, we have a RD which is deciding the gain, and of course we have this ID. But out of these things there are some parameters which user cannot manipulate. When I say user cannot manipulate, this Kp, which is actually given by mu n into Cox, the mobility of the electron is not in the hand of what the user or the designer, and this Cox, which is the per unit area capacitance of the MOSFET, is also not in the user control. So these two parameters user cannot change. Of course, in dot model file, suppose if you just go over here, if you actually see in the dot model file, you are actually defining the value of Kp, but you are defining it as 200. You cannot say it as 0.2 micro. You cannot say it as 5000 micro. Now, these are all, there are some standard values which are typically available for a MOSFET. So user cannot choose at his wish, whereas W by L can be changed at his wish depending on the requirement, whereas this Kp cannot be changed. So that's what I mean by you cannot change this parameter. This W and L you can change, user has the control, and this threshold voltage also user don't have the control. So even though these are the parameters, user don't have the control on this, user don't have the control on this. So can user get desired value of AGs, or can select desired value of AGs? Yes, he has got the freedom. He can select his own W by L, and this is again VGS is at his disposal, and this VGS is realized using this, so that's why R1, R2 will decide, and he can select whatever RD, and of course he can choose whatever ID he wants. So of course in the previous design you might have seen that ID we took it as 400 microampere. It is left to the user how much he wants, and of course this ID is decided by as per this equation W bell and VGS. Now what we'll do is, so we will keep all of the parameters constant, we'll vary one parameter and try to see what is the impact of that on the entire response. So what we'll do is we'll start with, so this we know that this is 200. Okay, let me just rewrite this circuit as it is. So this is my circuit. So this is what we have it as 1.8 volt. This is RD, this is R1, this is R2, this is coupling capacitor, this is this grounded, V in. Okay, this we choose it as 200k, this is 100k, this is W and L is, this is 10 micro, this is 1000 micro, that's what we've chosen. So first we will actually vary this. So if we vary this, what will happen? If you vary this, then this will change, that means this will change, so VGS has to change. If VGS changes, what will change? ID will change. If ID change, what will change? This GM will change. If this GM will change, then AV changes. Can you see this VDS, which is nothing but, so what is one more equation here? So shall I write this VDS as VDD minus ID RD? So if I change R2 variation, R2 this R2 variation will make the changes in VGS, which will change ID, which will change GM, which will change AV, and this ID will also change my VDS. So this is the effect of all these parameters will get modified. VGS will change, ID will change, GM will change, so on so on. So let us see how do we achieve that, how do we see that. So this is 100k. What I'll do is I'll replace this by, within flower bracket, some name. I'll name it as RVAR. So this is a variable, I'm making it change, and I will use a command called as step param param. What is the parameter you're changing? You're changing RVAR. Let us change it from maybe 80k to maybe 140k with an increment of 10k. You can see this is what I'm trying to do now. So I'm changing this value of the resistor R2 from 80k to 140k in steps of 100k. If I run now, I can see what is this VGS, what is this VD, what is ID, and all those stuff. So what we'll do is we'll actually visualize only these DC parameters, that is VGS we'll see what is ID, we'll see what is VDS. So we'll see that. So we're not changing anything else. So what I'll do is I will run. Okay, I will not, okay, let me not see this. What I'll do is let me just take out this, I will delete the plots, I will rerun it. Now let me see what is VGS. Maybe for the time being, let me not apply the input. Let me make the input as 0 so that it will be clear. I'm not applying any input. Let me rerun it. Can you see this VGS voltage is totally different? So this is VGS, which is, can you see here, this is for 514 millivolt is VGS, and you can see next it is 558, next it is 600. This is actually 600 when RD is R2 is 100k. You can see next it is 638, next it is 675. So as we saw here, if you change R2, VGS is changing. So this is what is change in VGS. So can I see the change in current? I will add one more pane. Here in this pane I'll add the current. How do I add the current? What you can do is you can come here, this is your clicked, and let me see what is the drain current. Now this is what is drain current. Can you see this is drain current? So drain current is initially here, it is 130 microampere. You can go here to, this is, can you see it is 130, next it is 251. Can you see now it is 400. This is corresponding to R2 of 100k. Then this is, next it is 569. So you can see you have different drain currents corresponding to different values of R2. So we have seen this, we can see this also. So as R2 increases, VGS increases, as well as ID also increases. So what should happen to this VDS? VDS should actually reduce, because when the drop is less, you'll have more voltage. When the current is more and more through this resistor, then more and more drop happens, then VDS has to keep reducing. So what I'll do is I will add one more pane and I will plot VDS. What should I plot? I will plot VDS. That is this voltage. See here, the first parameter what I have is the maximum. Can you see this is for R2 of 80k, because 80k is my first value. This is my 80k is the first value. Where is that? This is 80k. For 80k I have this. Then you can see if I go down, this is for next value, which is 150, sorry 1.54, then it is 1.4. This is actually for 100k. So this is what we were getting earlier. Can you see this is keep going down here? Can you see this is reduced, it's reducing, 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 reducing. So when we actually increase the value of R2 from 80k to 140k in steps of 10k, VGS actually increased. So let us see what happens here. Let me just go back here and show you. As per these equations, if R2 increases, so naturally as per this equation, VGS will increase, ID will increase, whereas VDS will reduce. VDS will reduce. Now if I increase this, my GM has to increase. So GM increment, since GM is a value, you cannot see it on the scope, on the waveform, sorry, on the simulation, but the effect of GM will going to increase the gain of the amplifier. So what you can do is, so we will do the AC analysis. Sorry, let us apply some signal here. Now let me apply 10 millivolt. Let me apply 10 milli. Now this is 10 milli now. Okay, you can also apply it this way. Can you see here? This is 10 milli. Apply 10 milli. Now I will run it. Now I will remove this and see only the output. Let me run this again. Let me see the output. See here? So this is can you carefully notice the peak to peak of this signal? So let me just put it here. There are two cursors. Let me put one here, other one maybe somewhere here. Can you see this is peak to peak of 45 millivolt? This is for a value of R2 of 80k. The peak to peak is 45. The peak to peak is 45. If I go down, so now this is one value. The other value, can you see this is, now I'm just having, if you carefully observe this, so what is one observation you can make is, can you see the peak to peak of this green one is less compared to blue one and red one? This is slightly more, this is still more, this is again more, and this green is the highest peak to peak. So if you can notice one thing, the DC voltage is keep reducing, whereas peak to peak of your output is keep increasing. So what I want to say here is, why this DC voltages keep reducing? So we actually have a waveform something like this. So this is for the least value of R2. I had a waveform something like this. So this is somewhere here like this. So then if this is for 80k, so you had some voltage. So now because of this you had some ID. So there was some DC voltage. When this is made equal to 90k, now this current, this increase in R2 will increase VGS, that VGS will increase ID. If this ID increases, this drop increases, then this voltage slightly reduces. So this reduced. So since increase of R2 has increased ID, GM has increased, what will happen? This peak to peak amplitude has slightly increased. This peak to peak has slightly increased. Likewise, if a further increase, this comes down, this peak to peak again increases. As long as you are coming down, this is keep increasing. This is keep increasing. So that's what is the observation you can make here. This is the observation what you can see. Can you see here? This amplitude is least peak to peak. Next it is this much. Next it is this. This is slightly keep on increasing. Maybe what you can do is you can just do it for 80k. Maybe you can just do it for that also. I can do, instead of having these many waveforms, let us have very few waveforms and then verify the variation here. So what I'll do, I'll just go back here, do a different dot step. Instead of this RVA param. Instead of this, I'll make it list. List list 80k. Maybe make it 120k. We let this to be sufficient. So I'm just doing it for 80k and 120k. These are the two different values. Let me run now. See now. Can you see for 80k it is this, for 120k this much peak to peak. Can you certainly see there is an increase in the peak to peak of output voltage compared to this. So this is for 80k, you had some DC voltage, and this is for 120k, you have some DC voltage. Of course DC voltage reduces, but the peak to peak is going to increase. So whatever our assumptions we made here, so now this increase is due to increase in GM. This increase in GM is due to increase in ID. This increase in ID is due to increase in VGS. This increase in VGS is due to R2. So this R2 variation will have all these impacts. This reduces. Suppose if this increase, this will again increase, this will again increase, this will increase, this will increase. Only VGS will reduce. Then can we see what is the effect of this RD here? If this RD increases, what we'll do, we'll just see what happens to this. So now what I have is the same circuit. This is VDD, this is RD, this is VD, that is DC, and this is V0 output. Let me have this. Let me have it as 200k and 100k constant. Let me vary this from maybe 500 ohm to maybe 8k with an increment of course you can give randomly, or you can let us just decide what will happen. So what is expected here, because we have these expressions, so where all RD is there, so does RD will affect this? No, RD. So let us see what is the impact of RD on ID. What else you have? Of course VGS you have, you have GM, you have AV, you have VDS. So what are the equation you have for this VDS? VDS is equal to VDD minus ID RD, whereas ID is equal to half Kp W by L VGS minus VTO whole square. VGS is R2 VDD divided by R1 plus R2, and GM is under root of 2ID Kp W by L. What is AB? Minus GM into RD. These are the parameters. Now if I increase this, does this change? This is not having RD at all. So this is, as long as the MOSFET is in saturation region, ID remains constant. So this is no change. Does VGS change? Because VGS, I know that expression for VGS is what? This is VGS, which is nothing but this I have here. So VGS will also not change. Does your GM change? This is GM expression. As long as ID remains constant, GM also won't change. Does your AV change? Yes, AV is directly proportional to RD, so this will change. Does your VDS change? This is my VDS. This will also change. So increase in RD will not change this as long as the MOSFET is in saturation. That is a condition. As long as MOSFET in saturation, it won't change. Does this change? Unconditionally, this will not at all change. Does this change? This again won't change as long as MOSFET in saturation. So there is a condition behind this not changing. So there is a condition. The condition is MOSFET should be in saturation. As long as MOSFET in saturation, these two won't change. How about this? This will change as long as RDs keep changing. This will also change. Let us see the impact of that. So what we'll do, we'll go here. We'll just make again this as 0 for the time being. Let us make this as a variable one. Okay, what I'll do is, let me go here and change this to RVAR. Can give whatever name. So let me change this to 100k. Let me just change this parameter from RVR. So let us make it as, maybe make it 500 ohm, make it as 2k, make it as 8k, make it as some 12k. So these are different values of resistance you have, or you can just make it not list. You just vary from 500 ohm to 500 ohm to maybe 10k in steps of 1k. So this is a linear variation instead of a list. Let us give it so. Let us see what happens. So we shall observe these changes. So let us see what happens to this. If I will run this. Okay, let me not do anything now. Now let me run this. Does your VGS change? Okay, let me not do this dot tran. Let me do, okay, DC operating. Now let me run this. Can you see? And now I'm changing from RD from 0.5 to this. You can see this VGS is constant. VGS is unconditionally constant at 600. That's what we said. This is not changing at all as you change RD. Does your ID change? Let us see what happens. So now I'll add a plane. I'll add a plane here. So let me see what is the current. I will see. Can you see? ID is changing. This is my ID. So ID is, suppose if I just see here, ID is constant at 2 microampere. Let me take out this for the timing. Let me click on this. Can you see ID is 400 microampere here? This is 400. For a certain range, it is. Let me change this color. You can see it was said that there is a condition up to which it won't change. So that condition is saturation. So as long as MOSFET is in saturation, there is no change. But once the MOSFET goes into linear region, the current is changing. The current is changing. Current is keep changing. So this is what is that condition. So here the MOSFET is not in saturation. When the current is not 400 microampere, in this case the MOSFET is not in saturation. So you can see the current is now 370 microampere. So the MOSFET now is in linear region. It's now linear region. Now how about this? Okay, we have seen this. Let us see. Of course you cannot see this GM. Let us see the GM effect once we see the AC signal. Let us see what is VDS. What we'll do is we'll add one more plane. Let us include VDS. So how do I do VDS? It is this voltage. This voltage. Great. Now you can see VDS is also changing. This is changing because as you increase RD, VDS is reducing. Can you see this is reducing? This is reducing. So this is reducing. You can carefully note one thing. What is VGS? You have 0.6. So once your resistor come to a region, see now just have a look at this voltage, because this is VD. When VD is equal to 0.2, you can see now this is okay. How much is? So what I'll do is let me slightly make this change much more smoother. Instead of 1k, let me just make it much more smoother, and I'll just show you that. So let me make it maybe 100 ohm. For every 100 ohm, let us change, because this is not very smooth one. If you can see here, this is not a very smooth plot. This is not a very smooth plot. Let me just run it again. Now you can see much more smoother now. Can you see this is smoother? So now let us see. So whenever this, okay, let me just take out, let me add only one. See now, let me have one here. So on IM, on drain current I have one, on VD I have one. Suppose if I move this to, okay, you can just have a look at this. This is cursor 1. This is cursor 1 which is moving on VD. Whenever that VD becomes 202, whenever it is 202, at that point I have a current of, so how much is the current? So current you have at that point, because what is the resistance? Resistance is 3.99k. So at 3.99k you have a current of 400 microampere. Can you see here? If the resistance further increases, then MOSFET enters linear region and the VDS will go less than 0.2. So this will go less than 0.2. Here, can you see this is less than 0.2? Can you see it is 164 millivolt? Can you see the current has also started reducing from 400 microampere to lesser current? So this way, what we are trying to showcase here is, if you increase the value of RD, VGS is not affected, ID is not affected as long as MOSFET is in saturation. VDS is affected because VDS is keep reducing. It's keep reducing because as you increase this will entirely, as you increase this is keep reducing. This is keep reducing, and of course it also have a role of this ID will also be there. ID will be constant as long as MOSFET in saturation. If this reduces, then this reduction is much more sharper. So that's what you can see here. What you can see here is this is reducing, and then this becomes a different slope, and then let us see the impact of this AV here. So for that, let me apply the signal and then run it. So let me apply 10 milli and then run it again. See now. Okay, let me do dot trend. I have to do dot trend. I'll do this. Let me run it now. Can you see now? Let me not see the parameters because I'm just doing it from, let me stop this. So why you're getting these many waveforms is because I have given increment of 100 as the resistance. For every 100 ohm it is keep changing, so let me just give it as maybe 1k or maybe 2 kilo. So it will start from 500. Next it is, sorry, let me just give a space here. So it is from 500k, 2.5k, then it is maybe 5.5k or 4.5k, so on. So it runs like that. Okay, let me not have this pane. Let me just delete this. Let me delete this also. Now this is what is the change. See here, this is for RD is equal to 500. This is for RD is equal to this. See here, this AV here it is less. The peak to peak has increased, but here you can see the peak to peak has actually reduced. One thing is very curious to observe here. Just go back here and then try to see. If I, so what is the expression for AV? It is minus GM into RD. As your RD increases, as per this equation, AV should increase. But this is not an unconditional increment. If RD increases, then AV will certainly increase, provided the MOSFET is in saturation condition. So when does this MOSFET in saturation condition? When VDS is greater than VDS sat. What is VDS sat? So VDS sat is nothing but when VDS is greater than VGS minus VTO. In this case, when VDS is greater than 0.6 minus 0.4, that is greater than 0.2. Because I know that as you increase RD, not only AV increases, this VDS actually reduces. If this reduction of VDS goes, make your VDS less than 0.2, you're in trouble. Because the MOSFET goes into linear region for larger values of RD. Same thing is happening here. Just see here. This is for a value of RD is equal to 500 ohm. So you have some gain. can see it is more than 0.2 MOSFET in saturation. Now you have increased it to, okay, what I'll do is let me just go back here and then slightly change this settings. Now let me make it this is fine instead of having that as 10K. Okay, just give me 1 minute. Let us make it as around 6K. This is, I'll make it 6K, or maybe, okay, let us make it as 2K. Let me run it now. See here. See now, I had this, I have this, I have this. So for only one waveform I have this, there is a gain, but here can you see what is the VD voltage? This is output voltage. Can you see it's below 0.2? So for these three values of RD, the MOSFET is in linear region. That's why you are unable to see the variation, unable to see the gain. So how to get back that proper gain? Suppose if you make this variation, may not be 1K. If you make it, okay, 0.5K, then if I run it now, you can see. Can you see this gain is keep increasing from this to this, this to this, this to this. Can you see the peak to peak is keep increasing, and the maximum peak to peak is for this blue, whereas for this yellow you are not having a proper waveform, because for this it is around 0.2, it has to vary. When it is below 0.2, MOSFET is in saturation. So for values of this RD, which is, okay, can we just predict what is the value of RD you have now for this? So this is, first one is 500, next it is 1K, then it is 1.5K, then it is 2K, 2.5K, 4K, 4.5K, 6K. For 6K resistance, this is at 0.2, and this is for 6.5, then it is 7, 7.5, 8. So for any resistance more than 6K, or even for 6K, you are not getting a proper waveform. So what is the learning or outcome of this is, if you increase RD as per this equation, mathematically AV should increase, but there is a condition involved in that. For this to happen, the MOSFET has to be in saturation. So the question is, does the MOSFET doesn't remain in saturation as long as, suppose if you increase RD? No, it may not be there in saturation, because the increase in RD will reduce my VDS. If the reduction of VDS is such that if the MOSFET voltage here, if it goes below less than 0.2, you are in trouble. You are in trouble for this particular case. So this way we can able to see the impact of change in R2 and RD. So in the next video we will see what is the impact of W by L on the amplifier. Suppose, can you keep on increasing the W by L at your wish? Let us see that in the next video.